Hello, welcome back to my channel. Today we are going to discuss a sequence of numbers that appears very often in software development interviews. A Fibonacci sequence, a sequence of numbers where each number is the sum of the previous two ones. So it always starts with 0 and 1, and then each 0 plus 1 is 1, so that's the next number, and so on. What you will usually be asked to do in interviews is write a function that receives a position for which you should return the Fibonacci number. In this scenario, the function would receive 6 as an argument, and then it should output 8 because this sequence is a zero-based sequence, so 0, 1, 2, 3, 4, 5, 6. So at position 6 we have the value of 8. There are a few ways to implement this. Let's go through them. Let's first start by writing a file for adding some unit tests, because we need to prove our implementations with unit tests. So let's do that. As you can see, I have a Go, just a module file, and you can of course do that with go mod init and then your URL, and then you need to say go mod tidy. Right, so now let's add our test file, touch Fibonacci underscore test.go. As you know, all the test files in Golang must end with underscore tests. Right, so let's write some tests, and then let's write the implementation for the Fibonacci series. So we will have something like, first of all, package func test. We will rename this later to something better. Testing.t, and then this will be a test function. Now we have the testing package imported, so now we can say go test, and we see that there is a test passing. Our module is passing the test, but there is nothing inside the test, so let's also write something here. So let's do the implementation for the Fibonacci series. Touch Fibonacci.go, package main, and then we have a few implementations. Let's call the first one fib1, func fib1. So we receive a position, which is an integer, which is the position in the series that we are interested in, and we return an integer. This is the simplest implementation. So what's happening is that we need to maintain a sequence of the Fibonacci numbers. When the sequence has the length, which is the position that we are interested in, then we just return the last element, right? So what does that mean? That means we start this sequence of numbers, which is, a slice of integers which starts with 0 and 1. The Fibonacci numbers always start with 0 and 1. And what happens is that we need to write some code now that always adds to this sequence as long as the length of the sequence is not greater than our position. So we need to say for length of sequence is less than or equal to our position, keep adding to the sequence, is append. We need to add the sum of the last two numbers. When we are just getting started, the numbers will be 0 and 1. The last one will of course be sequence at length of the sequence minus 1. This is the last number in the sequence, and then we add it to the number before it, which is the length of the sequence minus 2. Okay, so we just keep adding to this one, and at some point this 4 will no longer be entered because the length will be greater than the position. So when that happens, we just return the last element. So we just say return, the last element, which would be length of the sequence minus 1. That's the position that we are interested in. So give me the last element in the sequence at that position, right? So if we write a test for this, our method is called fib1. So let's say we are making exactly this test. So we need result, or actual is fib1 of 6, and this should give us 8. And if it's not, then we need to fail the test. So if actual it's not 8, then d.error expected value of 8 at position 6. Okay, now let's run the test. Go test. All right, so as we can see, we passed the first method. So very simply, again, what did we do here? We're just storing a sequence of the Fibonacci numbers, which we keep adding to as long as we have not reached our position. At some point, we do reach our position, and we know that that's the last number that we are interested in. So then we just return it. Right. And we can also do this using recursion. So let's just duplicate this test. Oh, let's give it a better name. So this was testing fib1. Right, now we have a fib2, which we will write in a second. Fib2. Right. The same test, let's write this function. So we have func fib2, which receives, as usual, the position, which is an integer. And this time, the idea is that we want to recursively call this function. This time, we are not just going to do a for inside the function like in the first one. We are going to be calling this same function over and over again until we have reached our desired element. So how do we do that? To do that, we need to keep track of the sequence on every call, right? So this means we just need to pass it along. So we pass, this is our sequence of integers, and this is the return type. When we first call this function, and now it requires 2 arguments, we will send nil as the first call. Why is that? Because this will keep calling itself again and again, but the first call has no sequence. So we need to make a check. If sequence is nil, sequence is slice of integers with values 0 and 1. Okay, this happens in the first call of the function, and then is the exact same logic here. For length of the sequence is less or equal than position, the sequence keeps getting appended to with the sum of the last 2 items. So again, we have sequence of length of the sequence minus 1, which is the last item, and we add to that length of the sequence minus 2. But then what we do here is we return. So as long as we keep entering this for loop, we want to keep calling this function fib2, return fib2 with the same position, because that's a constant. But then we pass the updated sequence, right? Which we just changed here with the new item. Each iteration will add 1 item, will increase the length, and then when we go here, we check again. Is the length of the sequence less or equal than position? At some point, this will no longer be valid. So then we need to just return again the last element. So we will be return the length of the sequence minus 1. Right? So very simple. Now we go back to our test and then we check if it's working. So go test. Right, so as we can see, the same test passes for the second implementation of the Fibonacci. There's also a trickier method to solve this. So first, let's write the test for it. It uses recursion as well, and it's actually something that the interviewers want to see that you know. So we will be adding another test fib3. Right? We have a third method, fib3. And we just let's implement this final method. So what's going on here? This is a bit tricky. It's a bit of a trick, this method, but let's write it first and then we try to explain it. So we will have a func fib3, which receives an integer and returns an integer. So if n is 0 or n is 1, return n. We can actually say, if n less than 2. If n less than 2, then return n. So now what we do is we say a and b are the same function again with n minus 1 once, and then with n minus 2, we assign the invocations to these variables, and then we return the sum of them, a plus b. Okay. So it's a bit of a trick, and we will explain it in a minute. Let's see if the test. Let's see first of all if this works. So we have fib3, give me the position 6, and we expect an 8. Okay. Go test. As we can see, it works. So now let's try to understand what's going on here, because it's a bit of a trick. So this function is not exactly efficient, but it's good to know. It receives an argument, and it keeps calling itself always as long as n is 2 or greater than 2, right? So what happens here? If the only times when this function returns actual values is when it's less than 2. So if n is 1, then it returns. If n is 0, then it returns. But if you call it with something greater than 0 or 1, then it enters this part. And what happens here? So let's say we call it with 2. So I want position 2. As we can see, at position 2 we should get 1. When it comes as 2, is 2 less than 2? Well, 2 is not less than 2, so we don't enter this if. Then we call this function again with 2 minus 1, which is 1, and with 0. So when we call it with 1, it enters this if. If 1 is less than 2, which is correct, then it returns n, which was 1. So this, in this scenario, this will give us 1, and this will give us, it's 0, so this enters as 0. Here is 0 less than 2, yeah, then it returns 0. So that means that Fibonacci of 2 would be 1 plus 0, which is 1. And this is how we get to the desired value here. So what happens is that, let's revert back. N minus 1, N minus 2, and this was N. Right. And this was 6. So what happens, let's see, let's print it here a bit, try to understand a bit. So what happens is that this function keeps calling itself up all the time with lesser and lesser values from what you passed, until at some point it will reach a point where these values, where the invocation of this function always returns zeros or ones. So let's see this in action. So when we say go test, so we add one print line here just to see what's going on each invocation of the function. So now we say go test. Right? So let's examine a bit what happens here. As you can see, is it keeps calling itself again and again with lesser values until at some point it outputs ones and zeros. Because it outputs ones and zeros, at those points it actually starts to return the values. When it starts to return the values, it starts to add up. So it keeps adding up the result of these invocations. It's like a tree. It diverges, each call diverges into, let's say this was 10. Then it skips this if, because 10 is not less than 2. But then it diverges into two trees of calls. Fib3 with 10 minus 1 and Fib3 with 10 minus 2. And it keeps adding until at some point it starts to return actual zeros and ones. And then it starts to add everything up. That was it. I hope it was helpful. See you guys next time.